Hi guys, so in this video we're going to be covering the world of alcohol, carboxylic acid, carbonyl compounds, and if possible nitrogen compounds as well. So we'll start from here. So we have propane-2-ol as we synthesize from propene. So if you recall, it's corn sulfuric acid 0 degrees followed by boiling with water or steam. Right, so now we're going to follow the arrows up. So the first reaction over here is redox reaction. So what's the reagent condition? The reagent condition is just sodium metal. Right? Why is it a redox reaction? Because firstly, my oxygen atom it loses a hydrogen atom, right? Because recall propane-2-ol, this hydrogen atom, that is O atom here, but then over here um, we have O minus and Na plus. So Na, its oxidation state went from 0 to +1. Yep. Okay, so it's a redox reaction. Now, the next part is that it's from an alcohol, secondary alcohol. So I'm going to talk a bit about a classification here. So it's very important that when it comes to alcohol as well as your RX, that you classify your compounds. So what's the primary, what's the secondary, what's the tertiary alcohol? So if you look over here, this is a primary alcohol. I assume the rest are all hydrogen atoms here. So this is a primary alcohol. Why is it a primary alcohol? Because I'm bonded to a carbon atoms that's bonded to two hydrogen atoms and an alkyl group. So the rule of thumb is that as long as my carbon is bonded to an alkyl group, then we know that it is a primary alcohol. So when we want to talk about secondary alcohol, for example, our alcohol group is bonded to the second carbon over here. So why is it a secondary alcohol? Because there are two alkyl group bonded to this carbon over here. Okay, so then what is a tertiary alcohol? So we just use the same example again, but now I have this. So I'm bonded to carbon number 2, but the thing is that I'm now bonded to 3 alkyl groups. So you can see here, alkyl group 1, alkyl group 2, alkyl group 3. Okay, so because there are 3 alkyl groups bonded, that's why I call this a tertiary alcohol. So whenever they ask you in elucidation and reaction stuff, it's very important that you classify it. And then maybe if they ask you about the naming. So it's secondary alcohol, primary alcohol. Okay. Now, so from an alcohol, it can be converted to a carbonyl compound. So I'm going to talk to you about why what kind of alcohol can undergo this oxidation reaction. So for this reaction, only secondary alcohol and primary alcohol can be oxidized to form carbonyl compounds. So if we were to look at here over here, if we were to so-called think if it's possible for a tertiary alcohol to become a carbonyl compound, you realize that this carbon has ended up with 5 bonds, which is not possible. And even if you want to remove one, remove an alkyl group just to form this, it's not possible. You can only remove hydrogen atoms here. So, in respect, it's not possible to form an carbonyl compound from a tertiary alcohol, because the process of forming a carbonyl compound means that I must lose H atom, so that I can form a double bond, C double bond O. I must lose this and I must lose this. Okay, so this is how carbonyl compounds are formed. So similarly, if you were to look at a primary alcohol so this compound here, HH. Now I want to form an aldehyde. So I need to do that. C and H. Yep, so it's an aldehyde. So I must have an hydrogen atom here, and the H that was previously bonded to this O must be gone. So that's why I cannot have a tertiary alcohol becoming a carbonyl compound. So whenever elucidation question asks you, and you deduce that it's an alcohol that has been oxidized to form a carbonyl compound, you must say it's either a primary or a secondary alcohol. Now, when we come to our carbonyl compounds over here, it's an oxidation reaction because we are losing hydrogen atoms, right? So we actually have two choices which we can use. So we can either choose potassium manganate or we can choose potassium dichromate. But please note about the color change. So over here, if we use potassium manganate, it'll be purple KMnO4 solution decolorized. But if we were to use potassium dichromate, the orange dichromate solution decolorized to form a green solution. That's with your chromium 3+ ions. Okay, so but this for KMnO4 purple solution decolorizes to form a colorless solution. That's one thing you have to take note of. Alright, so now moving on to talk about our carbonyl compounds. Okay, so over here we have propan 2-ol. It's going to be oxidized to form our ketone. So the thing about oxidation of alcohol to carbonyl compounds is that secondary alcohol will be oxidized to ketones, and primary alcohol will be oxidized to carboxylic acid. But there's a special reagent and condition, must I say condition, yeah, and also a specified reagent to turn a primary alcohol into an aldehyde. Okay, so before we do that, we're just going to examine our secondary alcohol first. So it's KMnO4, like I said earlier, and yeah. So or we can use potassium dichromate as well. It must be heating, and sulfuric acid, and or you can use an alkaline medium as well. Okay. So now we have our ketone over here. This is called propanone. So when we name our ketones, we always end with a ONE, propanone, ketone, so propanone. So from propanone to this compound over here, we'll do the idle form, which is an oxidation. So we have NaOH aqueous iodine. Iodine aqueous, as well as warm. We do not want to heat because it will decompose our yellow precipitate. So this is a yellow precipitate that will be formed. So specifically what we can only react with is that our ketones, if it has a methyl group attached and an R group at the side. So this is how it works, only when I have a methyl group. So why is an aldehyde over here? Because this is a special case, a special reaction. It's only for ethanol. So for aldehyde, because it's an aldehyde. Therefore, we end with an Al. Okay, but because ethanol, it has a methyl group over here, so that's why it can undergo this idle formation. But all the rest of the aldehyde cannot undergo this reaction. Only ethanol. Okay, so then it will form this compound here. So it will form COO minus and R group, and just so happen our R group is a methyl group, right? Actually, this one it won't form this, yeah. So just take note. This is a bit different. So instead, it will be a hydrogen atom here. So the R group can be a alkyl group or a hydrogen atom, if I'm not wrong. Okay, so where does idle form also occur for our alcohol? So we have over here a propan-2-ol, which is also a methyl alcohol. So what is a methyl alcohol? So we have CH3, C, OH, H, and an R group. So R group can be a hydrogen or an alcohol group, if I'm not wrong. So a methyl carbonyl means I have a methyl group attached to this carbon over here. This carbon must be bonded to a OH group and a H atom. So this is a very, very specific one. And just so happen, our propan-2-ol fits this category. Okay, so if we were to go a bit here, if I... Okay. Yeah. Okay, that's fine. Okay, so yeah, if we were to follow along this arrow here, for this arrow, to form this compound specifically, we will of course use I2 aqueous, NaOH aqueous, and warm to form this compound. Okay, so the CO minus CH3. Please note that this is not just only limited to a distinguishing test if I want to detect the presence of a methyl carbonyl or methyl alcohol. By methyl carbonyl, I mean this structure here, where R is an alkyl group or hydrogen atom, if I'm not wrong. So you can tell this methyl carbonyl structure is kind of similar to methyl alcohol structure. Just that, yeah, alcohol is a hydrogen atom attached. Okay. Yep. So the thing about the formation of these idle form tests is that I'm going to show you like how they actually like what's the step-by-step mechanism to actually form our precipitate here. So this is quite applicable in like MCQ questions, like for example when they have some weird compounds that you're supposed to deduce that whether it can react to form your yellow precipitate, right? So I can see one application of this, like for example in the MCQ question that I saw quite earlier on. So it was something about replacing the hydrogen with deuterium. So they want to see if they incorporate it into the organic compound or something like that. Okay, so the way this triidal methane test, how did it actually work is that my hydrogen atom will be slowly substituted with my iodine atom. So if I were to see here, so for example I have this compound CH3, then slowly it will become substituted CH2I, then I have R, CO, CH, I. Two. Then RC, O, CI3. So it's a slowly substitution. So got to do that for a methyl alcohol. It's the same thing. So it will go all the way until it forms this. And then some reaction occurs that forms our this final product here that you were meant to see. Okay. So so I can have, so that means compound like this can still undergo triidal methane test under this idle form reaction, which is oxidation reaction. It can still occur because a slow substitution to form whatever that we need to form. Okay. So if we were to refer to here, so that's our idle form test. Okay, yeah. So moving on, we'll be looking at the reactions of our aldehyde and our ketones. So the first reaction that we know that we learn is condensation. So these are condensation reaction is what both classes of carbonyl compounds can undergo. So what you'll condense with is 2,4-DNPH. So what is 2,4-DNPH? I think sometimes quite a number of people don't really know how to draw 2,4-DNPH. So here's the compound. So we start off with a ring, a benzene ring. Then after that we have our two substituents. They are NO2 groups. And they're on position 1 and position 2 and position 4. So that's what's called 2,4-DNPH. 2,4-DNPH stands for dinitro phenylhydrazine. But you can just write 2,4-DNPH. It's a universally accepted name. So my position 1 will be this thing. It's a hydrazine group. So it's two nitrogen atoms here, and they're all single bonded. Then each nitrogen atom is bonded to a hydrogen atom. But this one is bonded to the benzene ring, and this one is bonded to two hydrogen atoms. So it's called 2,4-DNPH. So I undergo a condensation reaction with 2,4-DNPH. So what actually happens here is that, if I can just reverse this a bit. Okay. So both of my hydrogen atoms will actually undergo will react with the O of the carbonyl compound, be it an aldehyde or a ketone. I don't really care. It's a removal of a water molecule, therefore it's called condensation reaction. And then what actually happens is that my nitrogen atom, carbon atom, they will form a double bond. So if we can see propanone here, it will form this compound. And for your propanol, we'll form this compound here with 2,4-DNPH. So what's the observation? It's orange PBT. This compound here is orange PBT, the one I'm circling. So what is the reagent and condition? The reagent condition is 2,4-DNPH warm. Note, we are not using heat here because I think it will decompose the compound. I'm not very sure, but we use warm here. Okay, so the next couple of reactions are quite interesting. So so ketones cannot be oxidized. That is what we need to know. Ketone cannot be oxidized. Oops. Okay, so now looking at the reagents and condition. So we know that ketone cannot be oxidized. So aldehydes can be oxidized. So this is one way that we can do a distinguishing test between an aldehyde and a ketone by doing oxidation reactions. So what are the various oxidation reaction actually? So the first oxidation reaction that we is quite commonly known. It's just your typical oxidation reaction. So you can use KMNO4 or potassium dichromate. Okay, so this is the only compound that we can only use both type of oxidizing agent that we can to to form the products that we want to form. So we have H2SO4 equals, or we can have our um, yeah. If we want to form a carboxylic acid, then we need to use acidic medium. Okay, so that's our first reaction. Don't forget heat. Okay, so now the second part is where it gets a little more interesting. Okay, so there are actually two other types of oxidation reaction that our aldehyde can undergo. So first type is with our Tollens reagent. So if you recall, Tollens reagent, it gives our very beautiful silver mirror. So Ag as solid. Okay, so it gives our silver mirror. So for this Tollens reagent reaction, what are the reagents and your products? So very firstly, you need to have your silver diamine complex, as well as your hydroxide ions. Yeah, so I'm not missing it out. Okay, then the next one that you need to have for okay, so what the products of this is that we're going to form our silver mirror. So it's Ag solid. We have our ammonia gas, and we have our water molecules. So this is the product, and generally speaking, so this is the general equation. 2Ag Hg 2 plus 4OH 3OH. From your plus 2Ag plus 4NH3, and you have your 2H2O. Yep. Okay. So that's for your Tollens reagent. So this Tollens reagent is compatible for both aromatic as well as aliphatic aldehydes. Now the next one is when we use failing solution and warm. Oops, sorry, forgot to add warm here. Don't heat. Okay. So warm. And our observation will be a reddish brown precipitate of copper 1 oxide reformed if it undergoes oxidation reaction. So thing about this is that it can only oxidize aliphatic aldehydes. So aliphatic aldehydes is something like this. This is an aliphatic aldehyde. So we have a straight chain carbon. This yep. It cannot oxidize aromatic aldehyde. So what's an aromatic aldehyde? This kind of aldehyde. It cannot oxidize using a failing solution. So you can do a further distinguishing test between aliphatic and aromatic aldehyde using failing solution warm. Okay, so similarly it will form our this product, which this is our group, and they'll form our COO minus. So what are the reagents and what are the products? So this one is slightly simpler. We just have Cu2 plus ions, and we have our OH minus ions as well. As for the products, we have Cu2O, and we have our water molecules. So if we balance it, generally, we have 2 Cu2 plus, 5 OH minus, CO O minus. We have Cu2O and 3H2O. Okay, so that's for our oxidation of our aldehydes. So, so nucleophilic substitution is the next mechanism we'll be learning. The last one will be electrophilic substitution, of which under Evans. So under nucleophilic substitution, the main case study that they use over here is for electrophilic substitution of an aldehyde using CN. So the thing they're using here is HCN, so hydrogen cyanide. So if we can see here as an aldehyde. Okay, so I'm going to be talking about why nucleophilic substitution for an aldehyde. Okay, so over here, the carbon is actually electron deficient. Why? Because there's an electronegative O atom. So if you recall from chem bonding, the electronegative atoms are FON, like the more electronegative ones, right? Therefore, they can form hydrogen bonds. So we have this electronegative O atom here. Therefore, it pulls the electrons more towards itself, therefore leaving this carbon electron deficient. Therefore, we have our nucleophile, like Cn-, which can attack the highly electron deficient carbon atom. Therefore, we have nucleophilic substitution. So over here, our step one is we're going to show the dissociation of hydrogen cyanide here. So we have our H plus equals, now Cn- equals, you don't really need to show the state symbol, but it's basically it. So it's the weak acid, so it's going to be dissociating partially. So we don't want to just have very small amounts of our nucleophiles, so we're going to add more, right? So one of the ways we can add more is using NaCN, which can dissociate from A plus and Cn minus. Or alternatively, we can use NaOH plus HCN from our Cn minus Na plus and H2O. So this is to form more, produce more Cn minus ions. So we have two possible RNC which you can use here. So trace NaCN 10, 20 degrees Celsius, or you can just use cold, doesn't really matter. Or you can use HCN and trace NaOH. Yep, HCN. HCN must be in both, but you can use either trace NaCN or trace NaOH. Remember, use trace amount, right? We don't want to put too much Cn minus to the point whereby it shifts increase in concentration of Cn minus, which will shift the POE to the left to reduce it. We don't want that to happen. That's why we use trace amounts. Okay. Now, step 2 of our nucleophilic substitution reaction is going to happen when I have my pi bond electrons break heterolytically to my more electronegative oxygen atom. Therefore, you must show our dipole charge, delta positive and delta negative charge. Okay, so we have our electron deficient carbon over here. So the pi bond will break heterolytically to give to my oxygen atom, and my bond pair electrons on on carbon atom I explained earlier in Rx why it's C and not N. So it will attack our electron deficient carbon atom, and then it will form this intermediate product. So now I have my negative charge on O. Why? Because it gained an additional electron. Okay, so now moving on to part 2, the last step. Okay, so the last step of this reaction is that now I have my lone pair of electrons of O is going to attack my H atom from this HCN. Now you don't really need to show the delta positive, delta negative, because the electronegativity of carbon atom and hydrogen atom are quite similar. So just showing this will do. And then if the bond breaks heterolytically again, it gives you your Cn minus nucleophile, which is OH group here and a CN group here. And then recall for nitrile group, you can undergo acidic hydrolysis, alkaline hydrolysis, or it can undergo reduction to form a primary amine. Yep, so that's our nucleophilic substitution mechanism here. So next we'll move on to carboxylic acid, but before that I just want to show you this primary alcohol that we have over here. So CnH2n plus 1 OH, that's the general formula. This is propanol. So you don't need to write propan 1 or because it's on the first carbon here. Right, so just a quick one. How do we form an aldehyde from primary alcohol? Like I said, if we were to undergo full oxidation for a primary alcohol, it will become a carboxylic acid. So how do we stop that from happening? So we need to use a milder oxidation agent. So therefore we have to only use potassium dichromate with an acidic medium and heat with immediate distillation. So this is very, very important. Do not miss out on this condition here. Heat with immediate distillation. If not, you won't obtain your aldehyde. Okay, so now we're talking about our carboxylic acid. So how do we convert a primary alcohol all the way to carboxylic acid? You can just use directly KMnO4 equals we have our acidic medium and we have heat. You can use K2Cr2 O7, still the same, but you can just use KMnO4 directly. Yep. So now we are looking at our carboxylic acid here. So yes, our general formula here will be CnH2nO2. Over here we're looking at propanoic acid. Okay, so carboxylic acid can undergo quite a number of reactions over here. So the first one that we'll be looking at is our distinguishing test. So how do we distinguish carboxylic acid from any other compound? Now if you recall, carboxylic acid is like the only so-called acidic aliphatic compound here. I say aliphatic. Okay, aliphatic. So in this case, we can add either NaHCO3 aqueous or just Na2CO3 aqueous. If you recall your O level carbonate and acid, it will produce our HCO2 gas, right? Then we have our CO minus and then we have H2O. So the only way to test is that you will see effervescence and the gas evolve forms a white PPT in lime water, which is calcium hydroxide. Please write out CaOH2. Okay, so with that, we're done with the distinguishing test. Next, we can undergo our redox reaction. What we need to do just sodium metal, or we can add NaOH equals 2. That'll work. But please note that we won't use Na as our distinguishing gas. So even though it produces hydrogen gas, which I forgot to mention earlier in alcohol, please note that even though it's hydrogen gas produced, effervescence observed, and it extinguished like the top sound, we don't do that because in laboratory using sodium metal isn't safe at all because it's very, very, very reactive. So we try to avoid that. Right, so we don't use NaS sodium metal as our distinguishing test. So we just use carbonate instead. Okay. So now my carboxylic acid, what other reaction it can form? Let me talk about esters first. So the first one of the reactions that carboxylic acid will react with my alcohol to form an ester. So the reagent condition here is corn sulfuric acid, heat. Now why is it concentrated sulfuric acid? Because it is a dehydrating agent. Over here we are undergoing a condensation reaction to form an ester bond. Condensation reaction between my OH group here of my carboxylic acid and my hydrogen atom on my alcohol. Okay, So this is actually a reversible reaction. So whenever you write it down in the equation, please make sure you include the half arrow, a reversible arrow. Only for the formation of ester from carboxylic acid and alcohol. So this is our ester here. So the way you name it is something IL, something OH. So where does the IL, where does the OH come from? So IL represents the alcohol, while OH represents the carboxylic acid. So then you ask, oh, where does the H2O, OH and the H in the H2O come from? So think of carboxylic acid as the very, very generous one that gives. So my OH in the H2O will come from carboxylic acid, while think of alcohol as a bit more stingy. So my hydrogen atom will actually come from my alcohol. So the O in the ester bond that you see here, this O here comes from the alcohol. So that means this segment represents the alcohol. Then this segment represents the carboxylic acid. So that's how it works. So our propanoate is how we name it. So it's the alcohol, YL, and O8. Okay, so this acidic this ester here can undergo hydrolysis. So hydrolysis is the breakage of this OCO bond. Okay, so go back to your individual components. So number one, this is our acidic hydrolysis. So remember, acidic hydrolysis, we use sulfuric acid and we use heat. Next one, CO minus, which means it's been neutralized. We use an alkaline medium, so NaOH aqueous, and we use heat. Now lastly, for our reduction reaction, now this is very, very special. So keep a lookout for this. Lithium aluminum hydride, dry ether. Okay. Alright. As I was writing this, I kind of like forgot to mention something. So give me a moment. I'll go back to that. So oops. So give me something. I'll go back to that. So my carboxylic acid here is propanoic acid. So yes, I'll form an alcohol as well as propanoic acid. But recall this lithium aluminum hydride can reduce alcohol. It will reduce carboxylic acid all the way to an alcohol, primary alcohol in this case. So I will have two alcohol products, and just nice because I form it from propanoic acid and propanol, I'll get two molecules of propanol. So this is very, very special. Yeah, let me retrace back to our carbonyl compound. So the thing about a carbonyl compound is that it's very, very special. In that case, we have actually two yeah. Okay, so for our reduction reaction, we can use our two reducing reagent, and this sodium borohydride can only be used to reduce our carbonyl compounds, only carbonyl compounds and nothing else. So we cannot use it to reduce alkenes, because what these reducing agent actually produce is our hydride ion, which is a nucleophile. So if you recall, alkene is electron rich, right? So if this electron rich region will repel my nucleophile. So I cannot use these two reducing reagents for this purpose. The reason why we use lithium aluminum hydride most of the time is because this is a stronger reducing agent. So why is this so? So one of the arguments is that, so if you recall, chem bonding. So over here in chem bonding, what it said is that so over here in chem bonding, because the strength of our bonds depends on the effectiveness of the orbital overlaps between our two atoms that's involved in the bond. So aluminum versus boron, right? Now, why is aluminum a stronger reducing agent? Is because it releases more of your hydride ions, and this can be related to a weaker bond strength of the ALH atom, ALH bond. Why is it a weaker bond strength? Because aluminum, it has a larger atomic size, so my orbital is more diffuse, so therefore it's a weaker overlap, less effective overlap, so for it's a weaker bond, and yeah, it breaks more easily and gives more hydride ions, so therefore it reduces my compound much more strongly. So therefore, lithium aluminum hydride is used most of the time because it's a stronger reducing agent. Okay. So, we, as a rule of thumb, we can always use lithium aluminum hydride in dry ether. For sodium borohydride, you don't need to do you don't need to put dry ether. Only for lithium aluminum hydride. Okay, and as a rule of thumb, we use lithium aluminum hydride most of the time, for all scenarios, most of it. Yeah, we can use it to reduce alkenes. For alkenes, we can only reduce it using our hydrogen gas, nickel catalyst, as well as heat. Okay, so retracing our steps, let's go back to our carboxylic acid. So what are the reaction that can undergo to form? Okay, so let's just go back. Okay, so if you recall, the formation of an ester from carboxylic acid and alcohol is a reversible reaction. So same for this. So for example, I have a CH3OH and I have a ethanoic acid. Oh, just draw propanoic acid. Okay, so basically it's a reversible reaction. Yep, so CH3 CH2COO CH3. Yep. Okay, so in this case, so this forward reaction is a condensation reaction, so we use corn sulfuric acid and heat. But the backward reaction is a, what do you call that? It's a hydrolysis reaction. Yeah, hydrolysis. So we add a water molecule to the bond, you break the bond, then it will be using sulfuric acid and heat. Note that here, when we want to form the bond, we need to use concentrated, but when we want to hydrolyze the bond, we just use aqueous will do. Okay, so that's how we form. So from our carboxylic acid all the way to an acyl chloride. So over here we have our propanol chloride. This can also be a Br as well, but for our case, we just stick to propanol chloride, acyl chloride. So how do we form this? So our OH here can actually undergo a nucleophilic substitution. Why? Because this carbon is actually electron deficient. You can see here, this is an electronegative atom, and this is, I guess, kind of an electronegative group. Kind of. Yep, so my carbon here is actually electron deficient. So my nucleophile can readily attack to undergo nucleophilic substitution to form my acyl chloride. So for here, we're going to use PCl5. Now you can use PCl3 heats as well as Cl2, that's fine as well. Okay, but we can use PCl5. Please note that for PCl5, it's an anhydrous, so same for SOCl2 as well. But you don't need to say anhydrous, you can just say PCl5, and we don't put an aqueous for PCl5, it's for a reason, right? So now I've formed my propanol chloride, and then recall my propanol chloride can actually form an ester as well. So this is of course plus an alcohol, so the alcohol I choose to use here is propanol. Nope. H2OH. So we use propanol here. But what actually happens is that it will undergo an elimination reaction. So we highlight here Cl and a hydrogen atom, then it will be eliminated from our HCl, but then the ester bond will form. This is the OCO. Okay, so we just need to add our alcohol here. We don't need any heat or any salt whatsoever, because by nature you should know that acyl chlorides are very, very reactive. And also, acyl chlorides are the most acidic when compared to carboxylic acid. Why so? Because when it reacts in water, it will form our carboxylic acid. So I think I forgot to write here, but it's okay. So CH3, so it's from our propanoic acid. All you need is to just H2O liquid, right? Don't need heat or anything because it's very, very reactive. Then it will form our HCl. So whenever when the question asks you, compare the acidity, and you see a acyl chloride, they say why is it most reactive? Most acidic. Must say that it forms readily undergoes hydrolysis water from a carboxylic acid, which dissociates from our H plus ions. But more importantly, is our HCl, which dissociates fully in water to give our H plus and Cl minus. And HCl is very, very acidic. So that's why you have your propanyl chloride being the most acidic here, acyl chlorides. Another reaction you can undergo is our reduction reaction. So over here we use lithium aluminum hydride in dry ether. So we add 4 hydrogen atoms, and it forms an alcohol as well as our HCl gas. Okay, so if I were to compare the acidity of my carboxylic acid and our alcohol, we can look over here. So over here we have our ethanoic acid, as well we have our ethanol. So we look at ethanoic acid first. So it dissociates, the H plus dissociates from this carboxylic anion. Okay, so what actually happens here is that this negative charge is actually dispersed over the OCO bond, right? So the keyword is the negative charge is dispersed over the OCO bond. Now, because the negative charge is dispersed, it's actually more stable, and because it's more stable, is the dissociation of H plus is actually more readily favored. But if you look at over here, it's ethanol. When it dissociates in water from our alkoxide anion. Here, if we contextualize it, it will be ethoxide anion. You see here that of course there's a negative charge here, but over here if you look at the group that's bound to it, it's an alkyl group. This is an electron donating alkyl group. So what it actually does is that since the electron donating, it doesn't help either, it further intensifies the negative charge on my O minus. Yeah. So because it intensifies the negative charge, it's actually less stable. Therefore, the dissociation of H plus from an alcohol is not so much favored. Yep. So this one is least acidic, and we consider it as almost a neutral compound. Alright, because the extent of dissociation of H plus is very, very, very small. So the main idea is the dispersal of negative charge. So recall earlier that this mechanical fluid and all these, when we form carbocation ion intermediate, is the dispersal of our positive charge. So similarly here, when we talk about anions, it's about the dispersal of negative charge. So the more that we disperse it, the more stable it is. So the idea is the same. So over here, when we're looking at our special reaction, the first compound that we focus on is called metanoic acid. Okay, so the first reaction here is called dehydration reaction. So C is the removal of water molecule. So what actually happened is that my CO2, CO will form, and then my H2O will form from here. So it gives a carbon monoxide and a water molecule. Second one is called an oxidation reaction of the reagent condition corn sulfuric acid. Yeah. Okay. And heat as well. Okay, so the next one is a strong oxidation reaction. So we call an aldehyde, it's not aldehyde, sorry, metanoic acid. In this case, it can be oxidized. It's a very, that's why it's called special reaction. So it can be oxidized by KMnO4. So you have your H2SO4, plus and you have your heat as well. Okay, so they will form CO2 and H2O. So actually it will form CO, but then CO will be further oxidized to form CO2. So the next reaction is similar to like your aldehyde, aliphatic aldehydes oxidation reaction. So the first one that we have here is our toluene reagent. So we'll add 4OH minus. Okay, but you see the compound that we form here is very different. So it doesn't have an R group. Okay, so it's gonna be carbonate anion. So I put a plus here. It's not for the positive charge on carbon. It's just because I ran out of space to add my compounds. But so what are the products we have? So we have 2 AgS plus 4 NH3 equals, and we have our 3H2O. Yep. So that's with our toluene reagent. And warm. Next we have our failing solution and warm as well. So reagent conditions 2Cu2 plus, and you have 6OH minus. Okay, you have CO3 2 minus again, you have our Cu2O, and you have our 4H2O. Yep, so that's how it formed. So our next special reaction is concerning with ethane dioic acid. So we call the last time we saw ethane dioic acid is under alkene, but it's a special reaction because it will be specially oxidized. Okay, so the first one we're talking about is our dehydration reaction. So dehydration reaction be here. Oh yeah, and I forgot to mention that for metanoic acid, the more commonly asked question will be our oxidation, strong oxidation. So similarly for ethane dioic, it will be our strong oxidation as well. But it's good to know the other reactions as well. So for ethane dioic acid, when they undergo dehydration reaction, so this is the compound that it will form. So it will form a carbon monoxide gas, then it will form a CO2 gas, and it will form water molecule. This is how it goes, and it's like this. Yep, so that's dehydration. So undergo so same reagent condition again, corn sulfuric acid, and use heat. What a lot of people mistake is that when they put corn sulfuric acid, then they put aqueous, which is very contradicting. So no, either you put corn sulfuric acid here, or you can do sulfuric acid, corn. Okay, so the next one is oxidation. So we know with our KMnO4 equals sulfuric acid equals, and we have our heat. So strong oxidation, as we've seen in alkene as well. So it will become this. Yep, so it's nothing new. Okay, so the next one is it's our nucleophilic substitution reaction. So over here we just use PCl5, but we need 2 moles of it because we have 2 OH group to sort of be substituted with our chlorine atoms. So then we have 2 moles of everything else. Okay, then our last reaction, this is under kinetics as one of the autocatalysis reaction. So Mn2 plus is your autocatalyst. So the mole ratio is 5 to 16 to 2 to 2 to 10 to 8. Right, so this is the mole ratio. I've rarely seen this being asked, but it's good to know nonetheless. Okay, so that's our special reactions. So now I'll be moving on to nitrogen compounds. Okay, so the only way to form nitrogen compound is when I react my acyl chloride with one of the following compounds here. So we can react with ammonia, we can react with a primary amine or a secondary amine. So before we talk about the classification of our amines, let's first understand why I can only react with these and not something like this. But these are our alkyl groups. Okay, so when I want to form amide bond, amide, right? This is my amide linkage. So it's O, C, O, N, H, or it can be an R group as well. But what I form here is the elimination of a molecule. This is N. Yep, so over here, my HCl is being removed. So the H so the H comes from the nitrogen atom, and the Cl comes from my acyl chloride. So therefore, I must minimally have one H atom on my nitrogen compound that I'm trying to react with this acyl chloride to form my amide. Okay, so therefore, with NH3, primary amine or a secondary amine, then we form this. Okay, so what constitutes a primary, what's secondary, what's tertiary amine? So it's kind of similar to alcohol again. So the whole idea on how many R groups is attached. So when I look at my primary amine, see one R group attached, so this is a primary amine. So if I have two R groups attached, this is my secondary amine. And if I have three R groups attached, this is my tertiary amine. So you can kind of see like the difference here. It's like, for example, like your tertiary amines, your tertiary alcohols are the one that's like not really like going to be reacted a lot. So whenever they ask for like classification compound or you detect this in amine, make sure you state what is the classification. Very important. Okay, so now from amide we can actually do this reaction here. So if we have this amide over here, which is actually formed from NH3 and our propanol chloride, sorry, we can actually do a distinguishing test between this compound here and, for example, a primary amine. So how can we distinguish? All we need to do is add sodium hydroxide, aqueous, and heat. So what we're going to do is we're doing a alkaline hydrolysis. So it will break this bond, and then we'll add a H back to here, and we have our OH to here. So forgive me my CO minus because it's an alkaline medium, and with NH3 gas. So NH3 gas, actually, if you see, a lot of people tend to just think there's effervescence, but no, because NH3 is very, very soluble, therefore effervescence is not observed, but there is a gas evolve. Gas evolve turns damp red litmus paper blue. So this is like your standard inorganic whereby ions. You can use this as a distinguishing test only when you have this part here. So they won't really ask you to, like, for example, if I have an R group and then I have H here, they don't really ask you to distinguish from a amine. So but when it comes to this, yes, there's a possibility they'll ask you. Okay, so now the last part of our reaction for amide is our reduction reaction. So we use lithium aluminum hydride in dry ether. Okay, so what it will do is that it will use my CO bond to CH. Now I don't care about what N is bonded to over here, but it does nothing to that, okay? It only does something to the CO T double O bond. Okay, so now let's look at our amino acid. So in amino acid, we'll be looking at this structure over here. So we have our alpha carbon. So alpha carbon is bonded to an R group. I don't care, it's a side chain. Then it's bonded to a hydrogen atom, bonded to an amine and a carboxylic acid. So when you place it in the water, what actually happens is that it undergoes an internal acid-base reaction. Okay, so the hydrogen atom go over to NH3 plus 2. So then I'll lose my hydrogen atom here, but it's gone over to my NH2. So you have this plus and a minus. So then it will form an ionic compound. There's a genetic structure. So it's a very high melting point. So it will be called a zwitter ion. That's when it has undergone its own internal acid-base reaction. And it also acts as a buffer because, for example, if you add too much OH minus, then your so acid here, you react, and then it'll give back your amine. So, but if you have added too much H plus, then it will react with your O minus here, and then you just form your OH. So this is an buffer reaction, buffer solution as well. In some questions that may ask amino acid, for example, reactions, because it was one of the compound, okay, so it has NH. Yeah. So then this went on to form a bond with my COOH. Yeah. So then I form a compound with this. So this is an amide bond actually. If you look at it, so it's very very interesting. It's called an amino acid. So it's kind of different to as what we think of an alpha carbon, but yeah. So this is an amino acid. So it's kind of different. So after learning about all these, right? What's the application of, like, for example, okay, about our amides and amines. So what are the basicity, right? So we know amines are basic, but why are they basic? So we look over here, amines, and we recall under the theories of acid and bases, we have Lewis, we have Bronsted-Lowry, and we have our Arrhenius. Over here we're looking at Lewis. Okay. So when talking about Lewis theory of acids and bases, we're always talking about the transport of electrons. So when he's talk about bases, it means it's a electron donor, right? Electron pair donor. So because we have our lone pair electrons on our nitrogen atom here, it donates electron, so therefore it's called a Lewis base. Therefore, amides are basic. But if you look at an amide here, right? So this is your amide linkage. You find that what they call it is that it's a neutral compound. So why is it neutral? So if you mind here, it's not maybe not very accurate drawing here, but this is like when my 1s orbital of my hydrogen atom, my sp3 orbital of my carbon atom, but it's not very important. So if we zoom our eyes on this part here, so this is my, so we'll be looking at this part here. So it's my hydrogen atom, so it's my O, C, N bond. So OCN, so it's here O, C, N. So OCN here. So what actually happened, you can see that because this is a p orbital, it's a p orbital, this is a p orbital, this is a p orbital as well. So even though there's a pi bond over here between O and C, But because of the way that things are, and they are quite interlinked to each other, as you will learn under um, arenes later. So what it forms here is like it's interconnected, in a sense. So therefore, what actually happens here is that my lone pair of electrons actually delocalizes over the OCN bond. So when it delocalizes over, it makes it the lone pair electrons on N atom is actually less available for donation. As such, it is neutral. Oh wait, it's not less available. It's not available at all. Therefore, it's neutral. But if you look at your amine here, because it's an electron donating alkyl group attached to N, so this makes the lone pair electron N more available for donation. Therefore, it's basic. So when what they will do is that they will combine all the theories together with your acid base equilibria. So for example, if I have a compound here, I have a H2N, this C, I have this COOH, and I have a NH2 here. Okay, so then I'll have my pKa values assigned. So this has the lowest pKa value. Don't mind my handwriting. And this will have the highest pKa value. So pKa value is something like pH. Yeah, but specifically targeting towards um, the groups here. Okay, so what I'm talking about here is like this has like the middle pKa value in between the both of them. Why? Because if we learn under arene, COOH is actually an electron withdrawing group, right? So it makes this, in a sense, the lone pair electrons are so less available for donation. So therefore, it's less basic as compared to this. We have this amine group is attached by connected to a very huge alkyl group, which is electron donating. Therefore, with the highest pKa, which is means the most basic. So how do you apply this to like acid base action and acid base equilibria? So for example, if I were to be my pKa value is 9.8, this is 8.7, and I have a maybe 2.7. So for example, when my pH is 9.3, we think of pH as so-called like the state of neutrality, right? So like the pH 7, so-called the neutral ground. So anything, any pKa value below pH 9.3, so meaning we think of pKa value as the like so-called the neutral ones, like the pH 7. So we have a pH that's higher than the pKa value of COOH group and the NH2 here. So what happens? So what they are drenched in 2, and this one will be neutralized to CO minus. But because I have a higher pKa value for this amine here, so and my pH lower than this pKa, so it's so-called in an acidic solution, so I have my NH3 plus. Yep, so the compound will be this. And that's because they will ask you like in the titration curve, like draw what's the major product and stuff. So that's how you reduce the thing. It's just a general rule of thumb. Yeah. Okay, so this is pretty much it for the nitrogen compounds segment. So now next we'll be moving on to our arenes, and I'll cover everything like phenol, your phenylamine, and all the stuff from there on. Yep. So see you in the next video, and that'll be the last.